Okay, so let's start with today's session. So what we are going to do, we are going to solve the previous year question from GATE, and we will in this series we will solve the questions based on linear algebra. So we have the questions of linear algebra in mathematics and CS, IT, EC, double E, and maybe instrumentation. And so what we will do first, we will solve the mathematics paper. So whatever the linear algebra question is in the mathematics paper, we will um, go through it year by year. So today we will be solving 2023 linear algebra questions. Then so we will try to solve last maybe 10 year or question. Once we are done with the mathematics, then we will jump to CS, IT, then EC. Okay, so let's start with the today's session. So let's look into question. So the first question is question number 19, I think. Okay, so 14, 15, 16, 19, yes. So this is the question. So in the question, it is given matrix M, and consider the following statements. That P statement is that M to the power 8 plus M to the power 12 is diagonalizable, and Q is M to the power 7 plus M to the power 9 is diagonalizable. So which of the following statement is correct? So first of all, this matrix M is given, right? So we can diagonalize this matrix M uh, when we have uh, n independent eigenvectors. So here this is 2 by 2 matrix, right? So this matrix is diagonalizable when we have two independent eigenvectors. So if we have two independent eigenvector, then we can diagonalize M. And after, so how that diagonalization will look like? So that M can be written as some matrix S, some matrix lambda, and S inverse. So let me just explain you what is this S lambda and S inverse. So this S is the eigenvector matrix. Eigenvector matrix. So what we do that suppose in this case, if we get the two independent eigenvector, then what we will do, simply we will put those two independent eigenvector column wise, then we will call this matrix S, right? So and this one is the inverse of this matrix. Now this lambda is the diagonal matrix, and this lambda has a form. So lambda is equal to, it is diagonal matrix, so in this case it will be 2 by 2 diagonal matrix, and here in the diagonal, at the diagonal position, all the eigenvalue will sit. So lambda 1, it will, so in this case it is 2 by 2, so we will have the two eigenvalues. So lambda 1 and lambda 2 will sit at the diagonal, and other elements will be 0. So this is lambda. So I hope that how we can diagonalize a matrix, then you got the idea, right? So first of all, we will have to check this, if this M is diagonalizable or not. So for that, we will have to check that if we are getting two independent eigenvector. So it is easy to check. So first of all you will have to find the eigenvalue, so lambda 1 and lambda 2. So how you can find this eigenvalue? It is simple that you can simply write 4 minus lambda and minus 3 and 1, 0 minus lambda. Now from here what you will do is you will take the determinant of this, and this should be 0. So from here you will make the characteristic equation, that will be 4 minus lambda times minus lambda and plus 3 is equal to 0. So from here what you will get is lambda square minus 4 lambda plus 3 is equal to 0, and if you factor this, then you will get that lambda is equal to 1 and 3. So lambda 1 is equal to 1 and lambda 2 is equal to 3. So corresponding to these eigenvalue, you will get the two eigenvectors. So even you can solve for the eigenvector. Let me calculate this eigenvector also. So what will be the eigenvector? So now what we will do, we will simply, first of all we will calculate the eigenvector corresponding to lambda 1, that is lambda 1 is equals to 1. So here just we will put lambda equals to 1, and we will get 4 minus 1, that is 3, and minus 3, and here 1, and here it will be minus 3, sorry minus 1, because lambda is 1, right? So now what you will look is for the null space, right? So whatever the x1 x2, so here so that null space would be that x matrix will x vector will be 1 and minus 1, sorry 1 and 1, because if you take this x1 as 1 and this x2 as minus 1, sorry 1, then if you do the multiplication you will get the 0 vector, right? So corresponding to lambda 1 you have the eigenvector, that is x1 is equal to 1 and 1, right? Same way what you can do, you can calculate the eigenvector corresponding to lambda 2 is equals to 2, lambda 2 is equals to 3. So for 3, how you will calculate? Same way what you will put here at lambda is equal to 3. So now, so 4 minus 3, 1, minus 3, 1, and 0 minus 3, that will be minus 3, and again you will look for the null space, right? So what vector will transform this matrix to 0 0? So it is simple, right? You can take here 3, so 3 times 1, and here 1, so 3 times 1, and so your other eigenvector will be 3 and 1, right? So 3 times and minus 3, so it will be 0, right? So you got these two eigenvectors, x1 and x2. Now these two eigenvector, if you check for the independent, then these two eigenvectors are independent, right? So they are not dependent. So these are the eigenvectors, right? Okay, so now we are very much confirmed that this matrix M is diagonalizable, right? Now the question is, M to the power 8 or M to the power 12 is diagonalizable. If so, how we can say that it is diagonalizable or not? If we can write this M to the power 8, if we can write this M to the power 8 plus M to the power 12 in this form, then we are sure that M to the power 8 plus M to the power 12 will be diagonalizable. So let me just we will have to check M to the power 8 plus M to the power 12, and we have already proved that M is diagonalizable. So you can say that this will also be diagonalizable and this will also be diagonalizable. So both statements are correct and you can mark easily. This is one number question. So I'm just describing you so that you have your own satisfaction, right? So let me, so if m is diagonalizable, then m to the power 8 will also be diagonalizable. And how we can write this m to the power 8 is, let me just write first of all m. So how we can write the m? We can write m as simply, we can write m as we can diagonalize m, right? So we can write s lambda s inverse. So this is m, right? But we will have to write m to the power 8. So what we will do, we will simply multiply this 8 times, right? S lambda s. So for each lambda we will do, right? So we will do this 8 times. Now if you observe this thing, so this one, right? This one. So s inverse s, what it will be? It will be simply identity, right? Again, here also you will encounter this s inverse s. So what will be the form of m to the power 8? What will be the form of m to the power 8? It will be simply m to the power s lambda to the power 8 and s. So this is s inverse. So this is m to the power 8. Plus same way, by same logic, you can write also m to the power 12 as s lambda to the power 12 s inverse, right? Now what you can do, you can take this as common, right? You can write is lambda 8 s to the power inverse plus lambda power 12 s inverse, right? Now you can also take this s inverse common. Then how you can write s lambda 8 plus lambda 12 into s inverse. Now look at this. This is two diagonals matrix, and if you add these two diagonals matrix, you will get some other diagonal matrix, right? So you will get some other diagonal matrix that will be some lambda 1, you can call it. So overall you see that you can write this summation as this form, right? And this is nothing but you have written this matrix as a diagonalizable form. You have diagonalized this summation matrix to this, right? So we can easily say that statement P is correct. And with the same explanation, we can also say that m to the power 7 plus m to the power 9 is also diagonalizable. So both statements are true. So according to that, option D is the correct answer, right? So how we can write this m to the power 7 and m to the power 9? So it is simple, simply with the same logic, right? So how it will look like? It will look like this. So it will be s lambda to the power 7 plus lambda to the power 9 into s inverse, and this is the sum of two diagonal matrix, and sum of two diagonal matrix will be again diagonal matrix. So again s and diagonal matrix and s inverse. So this is also diagonalizable. I hope you have got the answer with complete clarification. Okay, now let's move to another question, that is question number 34. Okay, so 28, 30, 31, 32, 33, 34. Okay, now in question 34, consider R4. So dimension of the space is given, that is 4 dimensional with inner product. So here it is given the inner product for x1 and y1. All right, let m is equal to this. So this set is given, right? This m set is given, and in this set, if you look at this set belongs to R4, right? So this the component of this sets are from the four dimensional space, and what it is given, one condition is that x1 is equal to x3, right? So if I ask you that how you can define this M in that four-dimensional space, so according to definition, what is given in the question, if you have to define this M, then you need x1, right? You need x2, and you need x3, and you need x4, right? So you need the four number, and additional one thing is given, that x1 is equal to x3. So if I, according to question, if you know this x1, then you also know this x3, right? According to question. So now if I will ask you, if you want to define this M, then how many component you need, or so you need only three component. Either you need x1, x2, x4, or you need x3, x2, and x4. Because if you know x1, then you know x3, or if you know x3, then you know x1, right? So now if I will ask you what will be the dimension of this M set, so the dimension of M set will be 3, because to define this set you need the 3 parameter to define this, right? If you know the 3 things, 3 parameters, then you know the M. So minimum we need the 3 component to define the M. So dimension of M set will be 3. I hope it is clear. Now let's move and read further. And M perp, so this is nothing but what we call is the perpendicular, and in short we call it perp. M perpendicular denote the orthogonal complement of M. The dimension of M perp is equal to. Now okay, so now here you need to know one concept, that is, suppose you are in dimension n dimensional space. So you are in n dimensional space, and if it is given that that one subspace is taking R component to define, or R vectors to define its own subspace, then its orthogonal component will take n minus R. So okay, right? So if you have given this n subspace, then here according to question, this M have the dimension 3, right? Then its orthogonal complement will have the dimension n minus 3, that is 3 minus, that is 4 minus 1, because here we are in the 4-dimensional subspace, 4-dimensional space, right? So 4 minus 3, that will be 1, right? Also, if you know already that if you are in any space, then the dimension of the given subspace plus dimension of the orthogonal complement, that is S perp, should equal to the given dimension of the given space. So dimension of the given space, that is n. So it should add to, so both the dimensions should add to this n. So whatever in the whatever dimension these two belongs to, so those two should add to the total dimension. So here we have given that M have the dimension 3, and we will have to find this x, and the total dimension is 4. So x is equals to 4 minus 3, that is 1. So the correct answer for this is 1. Okay, now let's move to question number 35. So question number 35 is easy one. So I think we can use some Clay Hamilton and we can easily find this value of the alpha. So let's find out. So what we will do, we will simply write the characteristic equation. So if you observe this, this matrix M is already in upper triangular, right? So so simply what will be the characteristic equation is 3 minus lambda into 2 minus lambda into 1 minus lambda is equal to 0. Now if you multiply, what you will get is lambda square minus 5 lambda plus 6 into 1 minus lambda is equal to 0. Now let's multiply this one too. So lambda square minus lambda q minus 5 lambda plus 5 lambda square plus 6 minus 6 lambda is equal to 0, right? So minus lambda q and 6 lambda square and minus 11 lambda plus 6 is equal to 0. Now you can simply put here at lambda the matrix M. So it will be minus m q plus 6m square minus 11m plus 6 is equal to 0. Now try to bring this to this form, this one. So what we will do, we will simply keep this as left side and left side, and everything we will bring to right side. So it will be m q minus 6 m square, so plus 11m is equal to 6, right? Now what we can do, we can multiply by m inverse both side, right? Because we need this m inverse. So it will become m square minus 6 m plus 11. So m into m inverse is I is equal to 6m inverse. Now you can easily compare this and this. So m square minus 6m, so alpha is 11, right? So the correct answer for this is 11. Okay, now let's move to next question, that is question number 40, I think so. Okay, so question number 40. Okay, consider the linear system mx equal to b, where m is given and b is also given, right? Suppose m is equal to lu. So we can decompose any matrix to lower and upper triangular. So where L and U are lower triangular and upper triangular square matrices respectively. Consider the following statement. The statement P is given that if each element of main diagonal of L is 1 1, the trace of U is 3. So trace of upper triangular, what will be the trace of upper triangular? So let's simply break down this M to L into U form. So how we can do? So M is given, that is 2 minus 4 and minus 1 and 3. So we can apply the elimination and we can knock down this guy and we can convert it into the upper triangular matrix. Okay, also we will track the elimination matrix also. So we can simply apply the elimination here. So the row first will be as it is, and to make this 0, what we will do, so we will consider this as a pivot. So this is the pivot element. So how we can make this 0 is we will simply So what will be the multiplier? Multiplier will be minus 4 divided by 2, that is minus 2. So what we will do, simply minus 4, so we will multiply minus 2 by this equation first. So minus 4 and subtract it from the second row. So 4 minus 2 times minus 2, so it will be simply 0, right? So it will be 0 as expected. And what will be here at the 3? So now we will 3 minus minus 1 into minus 2, so it will be 3 minus 2, so it will, here we will get 1, right? So also let's track the elimination matrix also, right? So that from there we will get the lower triangular matrix. Okay, so what will be the elimination matrix? So what we have done, that E21 we have applied the elimination to this guy, that is minus 4. So row 1 will be same as it is as the identity matrix, and row 2 will be what we have done. What is the multiplier? Multiplier was minus 2, so it will be 2 and 0. So this is the elimination matrix. So what I mean to say, that what we have done, we have applied this E21, and when we applied this E21 to this matrix, and then it got converted to upper triangular matrix. This is upper triangular matrix, right? So if you look at this, this is upper triangular matrix. Now so we have applied this. Now that lower triangular matrix is nothing but the inverse of this. How? So what we have done, we have applied this E21 to M, and it got converted to U, right? And now if we want this M back, then what we will do, we will apply this E21 inverse, and we will get this M back, right? So this lower triangular matrix will be nothing but inverse of E21. So lower triangular matrix will be simply 1, 0, minus 2 and 0. Okay, here it will be 1, not 0. So this is a lower triangular matrix. Now it is asking for the trace of the upper triangular matrix, so we do not have to calculate even the lower triangular matrix. And also if you see that the main diagonal of L is 1, so main diagonal of L is 1 we are getting, right? So trace of matrix U is 3, right? So 2 and plus 1, trace is nothing but the sum of the diagonal element. So trace of matrix U is 3, that is the correct, so P is correct. Now let's jump to the Q statement. What Q statement is asking is, for any choice of initial vector x0, the Jacobi iterates xk, where k is equals to 1, 2, 3, converges to unique solution of linear system mx is equals to b. Okay, so we will have to look, I think, is if this mx is equals to b have the unique solution. Alright, so it has unique solution, right? Okay, so b is given minus 2 and 5. So b is given minus 2 and 5, m is 2, minus 1, minus 4 and 3. So simply we can solve and look at if this system of equation have the unique solution. So 2 minus 4 minus 1 and 3, we will write this as augmented matrix. So here b is there. Now simply we will apply the elimination and we will find the value of this x, right? So if it is unique, if it is we will look that if this x is unique, or so it will be, let because this have the rank 2, so let me solve it first. So here it will be -2 -1 and -2, and here it will be 0, and here it will be 1. And so what we have done is 5 minus -2 into -2, right, because our multiplier was -2, so it will be 4. The 5 minus 4 is 1, right. So if you solve this one, then what you will get, so now you will do the back substitution, right. So x2 you will get 1, and 2 times x1 minus 1 is equal to -2. So from here x1 you will get -2 plus 1 divided by 2, that is -1/2. So a unique solution exists, so statement Q is also correct. Okay, one more thing, I am not very sure about this thing, right. Initial vector x0, the Jacobi terms, iterates, it converges to unique solution. So I am not very sure about this. You can verify it from book. What I am sure is that this linear system equation will have the unique solution. Okay, now let's move to question number 59. So next question in linear algebra is question number 59. Okay, 49. Okay, so this is question number 59. Let A be 3 by 3 real matrix with determinant itna is equal to 0, where I is equal to, and I is the 3 by 3 identity matrix. If determinant of A is equal to 3, then trace of A square. So it is asking for the trace of A square. So if you are familiar with this kind of expression, then you will know what question is asking. So okay, so this is nothing but when we, okay, so let me show you how, from where this is coming. So if you remember that if we have matrix A, and if we want to find the value of eigenvalue, if we want to find eigenvalues, then what we do, that A times x is equal to lambda x, and these x's are eigenvector, and this is eigenvalue. And from here what we do, that A minus lambda I times x is equal to 0. Now if you see that this is again a system of equation where you can take this as b and this is x, so bx is equal to 0. Now what you will look is for the null space, right, and also if any combination making this vector b, this matrix b is 0, that means this is not having the full rank, or you can say you will have some column or row that will be linearly depend on the some other row or column. So that means the determinant of this would be 0, and from there you solve for the to get the eigenvalue, right. So if you look at this expression, so this is nothing but what we are taking is the determinant minus lambda times I, right, equal to 0. So if you observe, this is nothing, this I is nothing but lambda, but that eigenvalue lambda is minus I, because here it is plus. So we have already found that one value of matrix A, one eigenvalue of matrix A is minus I. So and it will have the three eigenvalue, and one of the eigenvalue is the imaginary number, or we can say the 0 plus I, that is complex number. Then other eigenvalue will be the complement of this, right? So it will be plus 1, right? So this is I, right? And one more information is given, that the determinant of A is 3, and determinant of A is nothing but the product of eigenvalues. So that is 3, it is given. So from here, if you calculate the lambda 3, that will be I into minus I into lambda 3 is equals to 3. So from here, lambda 3 is 3, right? I square is minus 1, and minus plus. So we have got the 3 eigenvalues, right? Now it is asking the trace of A square. So it is not asking for the trace of A, it is asking the trace of A square. So we will use the diagonalization and we will find the trace of A square, and it will be simply the square of, so what will be the diagonal element if we diagonalize this A square, then what it will be? So it will be some matrix S that will contain the eigenvectors and lambda square, and this lambda square is nothing but the diagonal matrix, and in diagonal position these eigenvalue will be sitting, and we are taking the square since we are looking for A square and S inverse. So what will be the diagonal element of A square? Simply it will be the square of these, right? And if we have to find the trace, then we will simply add those. So trace of A square is equal to minus I square plus I square plus 3 square. So I square, that means minus 1, again minus 1 plus 9. So 9 minus 2, that is 7. So the correct answer for this is 7. Okay, now let's look at question number 60. Okay, so in this question, if you look